All right, lattice energy, lattice energy, lattice energy. Lattice energy is the energy holding a crystal together, an ionic compound, the crystal structure, as we call it. So, lattice energy, represented by capital U, is the energy necessary to break apart an ionic solid into its component ions as gases. So it's a slightly more complex thing than just the amount of energy holding it together. You basically have to boil the ionic compound in order to measure the lattice energy. You have to put energy in to pull those ions apart. So the lattice energy is a very big, very positive number. So what we're looking at, if you were to put it in terms of chemical reactions, you take a solid salt and you break it up into gases. So you go from solid sodium chloride to gaseous sodium and chlorine ions. Here we have, that's uranium 4 oxide getting broken up into uranium ions and oxide ions. Okay. So here we have lattice energies of some ionic solids. So you combine the cation in the vertical column here with the anion in the horizontal column here. Now, in order to understand the trends here, you have to understand or remember the math for, come on, bring it back up, there we go, for the attraction between ions. So this is the Coulomb equation. It is the force between charged particles. It is based on the charge of the one charged particle multiplied by the charge of the other particle divided by the square of the distance between them. So the bigger the charge, the stronger the attractive force between the two ions. The bigger the distance between them, the smaller the attractive force. So the smallest, smaller charges mean smaller force means lower lattice energy. Bigger charges means bigger force means bigger lattice energy. On the other hand, talking not about charge but about the size, the bigger ions mean that they just can't be as close together. Smaller ions can be packed close together. So smaller ions mean you're dividing by a smaller number, so the force will be bigger. Bigger ions, you're dividing by a bigger number, so the force gets smaller. So in terms of charge, bigger ions means bigger force. In terms of size, bigger ion means smaller force. Now, it's really easy to double the charge of an ion. You just take one step on the periodic table. That's right, Wesley. You dream your doggy dreams. But it's really hard to double the size of the ion. You have to move a significant distance on the periodic table. So charge will be the overwhelming factor there. So now let's go ahead and look at some of these guys. So lithium and fluorine. Lithium is one of the smallest possible ions. Let's go over to the periodic table. It's here in the upper left. And fluorine is definitely the smallest ion, okay, in the upper right. Okay. So they have a significant lattice energy. You take a step to the right here, you go from fluorine to chlorine. Well, fluorine is right here, chlorine is one below it. Then bromine, then iodine. Okay, so that is what we're looking at, dang it, on this chart. Okay, so every step here, bigger anion, as in terms of bigger radius, bigger ion, bigger ion. So as you can expect, the lattice energy goes down as you go from fluoride to chloride to bromide to iodide. Notice that these aren't huge changes, because even though the ions are getting bigger, they're not doubling, tripling, quadrupling in size. Similarly, we take a step down, we go from lithium to sodium. Sodium is one below lithium. The lattice energy goes down. From sodium to potassium, potassium is bigger still, the lattice energy goes down. But for every step down on the periodic table, we're not doubling or tripling in size, so it's not a huge decrease in lattice energy. Compare lithium fluoride to lithium oxide. Lithium fluoride is, a lattice energy of 1,000 kilojoules per mole. Lithium oxide is 3,000 kilojoules per mole. The oxide just has a much bigger charge. Okay. Notice it's not literally a doubling of charge. the math gets a little bit more complicated than that, because these distance equations and so on are the crystal structure changes, is all I'm trying to say. So we're not going to be literally asking you to predict numbers or anything like that. Instead, we're just asking you to make comparisons. Lithium fluoride to lithium chloride, well, you're just, changing the anion, and the chloride is the bigger size, so it has a lower energy. But lithium fluoride versus lithium oxide, the fact that oxygen has a 2- charge makes a huge difference. Okay, so it is going to be much, much, much higher. Similarly, we compare lithium fluoride to beryllium fluoride. Lithium has a 1+ charge, beryllium has a 2+ charge, so it goes from 1,000 to 3,500. Okay. Charge makes a really big difference. Size makes a small difference, is what I'm trying to say here. Then we can compare aluminum fluoride, that's at 5,200. So 1,000, 3,500, 5,200. We can also compare beryllium and magnesium. Magnesium is a larger size, so the energy goes down. Calcium 2+ is larger still, so the charge goes down. Meanwhile, aluminum 5,200. Boom, big jump. And obviously, the biggest lattice energy on this chart is going to be aluminum oxide, with the highest charges of your ions. So aluminum oxide, 16,000. Wow! There's a reason we use this in jewelry. Aluminum oxide is the crystal structure that gives us sapphires and emeralds and rubies. It takes a little bit of impurity to give it some color. I think sapphires are blue because of copper. Emeralds are green because of a different copper. And rubies, I think, are red because of oxygen. Not oxygen, because of iron. It might be chromium. But regardless, they get their brilliant colors because of things other than the aluminum oxygen. But the aluminum and oxygen give it a very, very strong, very stable crystal structure. All right. So you can't predict lattice energies, but you can compare them. And you will be comparing them based on the size of the physical size and the size of the charge. Okay? And charge makes a much, much bigger difference than size does. Okay? So when looking at two ions, worry about charge first. The size of the ions will only come into play if the charges are all the same. Okay? So for example, right here, we're comparing calcium chloride versus calcium oxide. Okay? In either case, it's something bound to calcium, so we look at the anions. We're comparing chloride versus oxide. Chloride is 1-, oxide is 2-. So it doesn't, the relative sizes of chloride and oxide don't matter. The fact that oxide has a 2- charge, that overwhelms everything else. Calcium oxide is going to have the bigger lattice energy. Calcium chloride is going to be lower. Meanwhile, down here, sodium chloride versus sodium fluoride, 1+, 1-, 1+, 1-. Okay, so all the charges are the same. So what matters here is the actual physical size of the ion, the actual radius. Fluoride has the smaller radius, chloride has the larger radius. And when it comes to the size of the atom, or the size of the ion, the physical size, smaller is better. So sodium fluoride has the larger lattice energy. Sodium chloride has the smaller lattice energy. So that is how they will ask you, that's the sort of problem they can ask you on a test. Compare two ionic compounds and predict which one will have the larger lattice energy. Okay? And charge makes a much bigger difference than size. So look at their charges, figure out what the charges are in the ions, and then just go with the one that has the biggest charges. If they're all the same, then you look at radius, and then smaller radius matters. All right. And that is it for lattice energies, and that is it for Chapter 3. I will see you